Hello everyone, I'm Sai Venkatakrishnan, PhD scholar in the Department of Computer Science and Engineering at IIT Madras. Today we'll be looking at week 10 live session for the course Operating Systems Fundamentals on NPTEL. So the agenda of the live session would be we'll be discussing some questions which pertaining to the week 10 lectures on the NPTEL portal which you would have watched previously, that is the virtual memory and all those concepts, TLB, page tables like that. The main aim of this live session is uh, to give you a platform so that you can directly interact with us and solve your queries and ask any doubts if you have in the lectures or in the concepts. Right. So let's get started then. So question 1 is as follows. The percentage of times a page number is found in the translation look aside buffer, which is the TLB. What is it known as? Is it the miss percentage or hit ratio, miss ratio, or hit miss?
Hit ratio.
Right. So the correct answer is, like, it's obvious. The answer is hit ratio. Hit miss, there is no such word as hit miss actually. It's just for added, just for fun, I guess. So option B is the correct answer for the first question. Any doubts in the first question? Right. I guess no doubts. If you have any doubts, you can unmute yourself or you can post the query in the chat box. Uh, just a second question. Every address generated by the CPU is divided into two parts, which are, is it the frame bit and page number, or page offset and frame bit, or option C, page number and page offset, or it's a frame offset and page offset? How
Page
would
number C.
option C, right? Any other guesses? Anyone else going for any other option or settling on option C itself? So, so the CPU, when it generates the address, it will be divided into, as Shashikant mentioned, page number and the page offset. So this page offset would be used to index into the actual page or uh, the frame with respect to the physical address. And this page number would be given to the TLB or the page table to obtain the actual frame number, which is residing in the actual physical memory. So this part is the virtual address space, and whatever you are actually accessing corresponds to the physical address space. So
So
option
this page offset is actually base address.
page offset is the base address. No, no. So page offset is like within this page, which value, which address I want, I'm actually referring to. So that the page offset used for. So this page offset is actually like uh, is based on the page size. So if the page size is say 4 KB, so 2 power 12 is 4 KB. So 12 bits would be used as your page offset.
No, I got it. I mean, actually, I was watching a lecture from another professor,
Right, right,
uh, currently the director of IIT Madras right now.
right.
Uh, so in his clarification, he was explaining that there is a page register which actually we need to add with the uh, entries in page table, and then we get the physical address. So I was just confused with that.
Okay.
But because here we are again, page offset.
Yeah, so finally, so the page register would be giving the page table base address. So this is your page register, means it will be storing the base address of the page table. This page number will be used to look up this page table and get the corresponding frame number. And this frame number is the actual physical address where this this page is located. And in that page, I want this particular value which is present at the offset, which is the page offset,
Okay, got it.
right? So option C is the correct answer. The other options are wrong. It's not frame, bit, and page number, all those things. It's page number and page offset. Any doubts in this question? If you are clear in this concept, it's important because the other questions are based on paging and all those things. Any queries? Okay, I guess so. No then. So question 3: when does a page fault occur? When a page gives some inconsistent data, or when a page cannot be accessed because it's absent from memory, or when a page is invisible, or all of the above.
B.
Option
B.
B.
When a page cannot be accessed due to absence.
Okay, right. So the correct answer is option B. When a page gives inconsistent data, it is nothing to do with page fault. It is just maybe you have some corruption in the memory, or some some error occurs in the memory, like uh, the how the memory holds the data. So everything is like a DRAM, right? In the memory, it will use those transistors and all those things. So say if it gets physically damaged or something like that, the bits whatever it stores in that memory might be corrupted, and then it results in some inconsistent data, or say some security attack or something. Some other process might go and write into some other process memory due to some bug in the OS kernel or something. In that case also, whenever the actual process reads the data, it will read this inconsistent or corrupted data. So that's what option A is all about. Option C is, I'm not sure what, whether it's possible, like a page is invisible. Maybe for security reasons, they would have just uh, marked this page as inaccessible forever or something. Like it's just invisible. So any process or anything, if it tries to access this page, it cannot access. But then also it will actually result in a page fault only. So I'm not sure what option C is all about. Maybe just to fill up the options, they have included this. So the correct answer is option B. If the page is not there in the memory, it's a page fault, and it should be fetched from your secondary storage, that is your storage disk, and it should be loaded into the memory to complete the access. That's when a page fault occurs. So option B is the correct answer. Okay. Any doubts in this question? Right. Then we'll move to the next question, question 4. So consider a paging hardware with a TLB. So you have a TLB, and assume that the entire page table, all the pages are in physical memory. So this is your uh, DRAM, and the DRAM consists of all the page tables and all the pages. So everything is present in memory. And now um, when you, so the CPU will generate the physical virtual address. The CPU generates a virtual address, and now it should be translated into a physical address, and for that it should be fed into your TLB to get the virtual what's that, the physical address and all those things. And if it's present in the TLB, the TLB is sort of like a cache with respect to your page table. So if it's present in the TLB, then you can directly use the page address, the physical address present in the TLB to access your memory, and that will take 20 milliseconds it's given. And if it's not present in TLB, then you have to go and access your page tables, and that will take 90 milliseconds because this page table is all present in this part in the DRAM itself, and that takes 90 milliseconds. And now it's also given the TLB hit ratio as 0.75. So 75% of the time it will take 20 milliseconds, and for the remaining 25% of the time the TLB fails because it don't have the entry, and it should go and search in the page table which is present in this DRAM, and that will take 90 milliseconds. Now the question is, what's the effective memory access time, average memory access time? Uh, so
So
anyone?
this,
Yeah,
this TLB is actually taking the data from PT, right? This is a kind of cache for page
yeah,
table.
yeah. So the TLB is getting like some same way how your cache is designed, right? The TLB will also have its own that replacement policies and number of sets, number of days, all those things.
No, no. I just want to just like page table, refers
Yeah.
to data of
So
actual data.
for your normal data, how you maintain the cache for page table, this is like TLB,
Okay, thanks.
right? So anyone trying to get the formula and uh, calculate the answer? Yeah, any guesses?
So you can say that like for the hit time was 75% is hit time, so we have 20 milliseconds for 75%, then remaining 25% we have 90 milliseconds. And that way we have to add up both the things.
Right. So let me explain the formula and those solution. So let's just write down. So the TLB hit is actually TLB hit time is 20 milliseconds, and if it's a fail, so a normal memory access time is equal to 90 milliseconds, right? Uh, 20 and 90, yes. So if it's a TLB hit, it's 20 milliseconds. If it's normal memory access, it's 90 milliseconds. And the TLB hit,
Sorry, for TLB means we have to access, right? Like we have to first check the TLB and then memory access.
right. So if a TLB access, just accessing TLB is 20 milliseconds, and a TLB hit ratio is 0.75. Okay, so now they are asking what's the effective memory access time. So let me just do like EMAT. So there are two cases, right? Here we assume like there are no caches. Okay, so it's just like the TLB is there, you have your page table and just your DRAM, that's it. So there are no caches as it is. So to calculate the effective access time, you should do like a case analysis, as in what will happen when there is a hit in the TLB, what will happen if there is a miss in the TLB, right? You should find out the access times separately using this hit ratio. Okay, so if it's a hit in a TLB, what's the access time to access any memory? So here every address generated by the CPU is a virtual address, and if we have to access the memory, we should translate this into a physical address and then only access the memory. So the first step, step one is for translation, and second step is the accessing the memory based on this physical address. So the step 2 is constant always, the time taken, because we don't have any caches or anything, always we have to access the memory. So that is 90 milliseconds for sure, step 2. Step 1 is where the optimizations are all occurring, because that's where the TLB is there and the page table. So for step 1, if it's a hit in a TLB, you just take 20 milliseconds to access and do the address translation, and the remaining 90 milliseconds you access the actual memory. But if it's a miss in a TLB, say if it's not present in the TLB, you will be having what you will be doing is you should access your page table to do the translation, and once a translation is done, you should do the step 2, that is accessing the actual memory based on that physical address that you got. And the page table is also present in your DRAM itself. So it's basically you're accessing the DRAM twice, once for the address translation to access the page table, and second to access the actual physical address that you get. So it is 90 plus 90, and also to first of all as get to get the result from the TLB, whether it's a hit or a miss, we should access the TLB, and then only we'll get to know whether it's a hit or a miss in the TLB. So anyway, we are accessing the TLB always. So it will be a 20 here also. You will be uh, using it when, even if it's a miss in the TLB, that 20 milliseconds you would be consuming, right? So if it's a hit in a TLB, you access the TLB and then you get the physical address and you access that physical address in memory. For a miss condition in the TLB, what happens is you access the TLB, you find out it's a miss, and to translate you access for the page table and you get the physical address and then you access that actual physical address in the memory. So this part is for address translation and this part is for the address accessing the actual memory. And same way this is for address translation and this is for accessing the memory. And now it is given the hit percentage is 0.75 and the miss percentage is 0.25. So what you should do is final formula is 0.75 into whatever this access time. So 20 plus 90 is 110 plus this one is 0.25. This is the miss ratio, which is 90, 90, 180, 20, 200, right? So if you just calculate and see, okay, what was to calculate? 0.75 into 0.75 into something plus 200 into 0.25. So it is 132.5. So this is the effective memory access time, and option A is the correct answer. Do you get the logic how we found out the effective memory access time? Any doubts in this? Okay. So in that case, let's move to question 5. So question 5, it is given we have a 1000 kilobyte memory. Okay. So this full thing is 1000 kilobytes, and the 1000 kilobytes uses variable partitions, as in it is not like say the user is accessing wants to allocate 20 100 bytes of memory space or something, 100 kilobytes or something. It is not aligned, as in there is not a fixed partition. So as in the paging based scheme, you will have pages of the same sizes like 4 KB, and each page is 4 KB, and the whole memory is split into pages. So but here it is given it's variable partitions, so you won't have a fixed size for the pages. So based on your process, whatever allocation it requires, it will allocate that much space and give it back to the user for consumption. So that is what variable partitions. And also note, they have mentioned there is no compaction, as in say if process 1 allocates some space over here and process 2 allocates some space over here, all these free space would not be combined together. There is no compaction at finally. So these allocated space won't be merged together and the free space all coalesce together. So that won't happen, right? So we have these two conditions, one variable partitions and no compaction. Now they are asking, currently two partitions of sizes 200 KB and 260 KB are allocated in the this out of this 1000 kilobytes, two partitions are allocated. So one partition is 200 KB and the other is 260 KB. And now what they are asking is what's the smallest allocation request in kilobytes that could be denied for. So the they are asking, so this P1, partition 1 and partition 2 have been allocated somewhere in the page in this full DRAM. The partitions have been allocated somewhere, so it can be at the starting itself, and the remaining is all free. or it can be somewhere in the middle also, like here P1 and here P2, and this will be free, and this portion will be free, or it can be like P1 at the start and P2 at the end, and in between it will be free. So it can be in any way it could be allocated, these two partitions, right? Or it can be, or the P1 and P2 will be at the bottom and the top part will be free. So in any way, so variable partitions, like it will be fine grained, as in whatever amount of at the address size that the process is requesting, that will be allocated. So the partitions P1 and P2 will be allocated, it won't be aligned or something, right? And the remaining space is free, and it won't be compacted or something, because they tell no compaction. And now they are asking what's the smallest allocation request in kilobytes that could be denied for. So say some new allocation request is coming for say 151 bytes or 181 bytes. Because of this no compaction or something, is it possible that any such request, a new allocation request, could be denied because of this non-compaction, and the total memory free space is not coalesced together, and because of that I cannot allow this new allocation request to take place. So, any guesses on what the smallest allocation request might be? With explanation. Any guesses? So, this how to approach this solution is interesting actually, because what they do, what's the approach is, we have to do like a case analysis, as in I just mentioned here, right? The since it's variable partitions, it's not fixed anywhere, it can be floating around the whole, it can be allocated from anywhere out of this 1000 kb. So one thing to note is say this P1 and P2 is here. So if you just uh, take the total allocated memory. So what's the total allocated memory? As in total allocated memory is P1 plus P2, which is 460 kb. And what's the free memory? The free memory is uh,
540.
yeah, 1000 minus P1 plus P2, which is 540 kb, right? So whatever your new request is, say if it's 151, or if it's 181, or it is 231, or it is 541, all these three have to be allocated from this 540 kilobytes free memory. Now the question is, because of these variable partitions and no compaction, this 540 kb memory might be split anywhere in any condition. It might be split in such a way that the free memory is 540 kb, but it won't be contiguous in nature to fulfill that new allocation request. So what's the smallest size that could be denied for in any one case? If that is true, then that's the answer, right? So let's just do a case analysis in that case. So say your P1 is at the starting of the memory allocation, and P2 is at the ending. So all your 540 kb would be present over here. So in this case 541 kb for sure you cannot allocate, because total memory free space is not is less than the new request. So 541 is for sure, it cannot be allocated even if there is free memory or everything is together.
We not this option because we are need the smallest one.
Yeah, so we are just ruling out this option. So 541 is not the correct number itself, it cannot be allocated for sure, okay. And now say, and the remaining three, so let's not consider 541 itself, okay. So in this, so this is case 1, let's assume, okay. and 540 is contiguous. So all these three requests 151, 181, 231 can be allocated within this free region. And now if say we consider case 2 where P1 and P2 are allocated at the top or bottom, and in the same way also the remaining space would be contiguous 540. So again all these three can be allocated because all these three requests fit within this free region, so it will go ahead and carry out the allocation. Now coming to case 3 where say some free memory is present over here, okay, and P1 is allocated, some free memory is present over here, and P2 is allocated, and some free memory might be present over here, okay. So assume this case. So now uh, what happens is this is a perfect case of like fragmentation, right? If you don't do a compaction, all these free memory are split, and if some memory request is coming which is greater than the largest free memory chunk, then even though the total free memory is uh, large enough to allocate the request whatever the process is requesting, since the free memory chunks are all split, it cannot go ahead and allocate that much memory for that request. So in this case 3, this 540 kb would be split between these free regions, and the free regions, it can be split in any way. There are like n number of possibilities. Just if you do like assume like it's split based on the average thing, right? Like 540 kb into three regions, it is split, so 540 by 3. So in that case it is what's that, 541, right? So each free memory region is of 180 kb. This one is 180, this one is 180, right? And now say these three requests are coming for 151 kb, 181 and 231. So 151 will go ahead, it will get allocated in any of the free chunks, but 181 and 231 it don't get allocated in the free chunk because both these allocations are larger than the available contiguous free chunk memory, which is 180. So out of these two, the smallest allocation request is 180, which was denied for. So the answer is 181. You could argue like even 150. Uh, what about 151? Like some other combination of P1 and P2, all those things. But the case is anyway, if you arrange this P1 and P2 and C, the free memory space which should be contiguous should always be greater than 150, right? And if all these 540 kb free space is split equally, right? Um, that's the average scenario. So if it's split equally, it is 180, and 181 or 231, both of these requests cannot be handled in this case 3. So 181 is the smallest allocation which is denied in case 3, and because of that answer B is the correct answer. And note that the question is not they tell that it could be denied for. So it's not that always if I request for 181 it should always be denied for. That's not the question. Is there any situation, any layout, possible layout of this partitions in the memory such that this 181 kilobytes could be denied for? So if the memory layout is like C1 or C2, 181 will not be denied for. Whereas in the memory layout of C3, the 181 kilobytes cannot be allocated. So that's what the question is about. Uh, did you understand the question and the logic, how we approach and solve it?
Got it. Thank you.
Nandan, any doubts in this?
Uh, no, sir. No, sir.
Okay. Good. Yeah, actually, these from here on, it's all like somewhat gate related questions. So these questions, thanks to Shashikant, he had shared it with me uh, today. So I just thought of including this because the other questions in the previous assignment were simple enough actually. The as in the previous week's offering of the NPTEL course, somewhat same. So I thought it would be interesting if I discuss these questions. So like, so if you have any doubts, just stop me, Shashikant or Nandan, so we can discuss it. Feel free to ask these doubts because even I'm just working out now. So right. So in that case, let's move to question 6. So in question 6, it's given consider a process executing on the OS that uses demand paging. Okay, and the average time for a memory access in the system is m units, and if the corresponding memory page is available in memory, and it's d units if the memory access causes a page fault. It has been experimentally measured that the average time taken for a memory access in the process is x units. Okay, which one of the following is the correct expression for the page fault rate experienced by the process? Okay, so how do we solve this question is, they have given, so everything is in terms of d, m, x, these units only. So you need not find out what x, d and m are. The answer what they are asking is for, question is for what's the page fault rate. Okay. So they have given three information. So one, it is demand paging.
If you can give me a brief regarding demand paging.
Right. So demand paging is nothing but same way how caches work, right? How main memory is to caches, it's like the same concept for the main memory and the secondary disk. So only when you are actually using, say, this is your DRAM, and assume like the process P1 is the virtual address space, which is totally, it will be allocated to that process. Say it is around 100 GB. Now you need not allocate all this 100 GB within the DRAM at the starting itself. You can just allocate whatever information or whatever data that the process uses frequently in the DRAM, and the remaining it can be just be stored in the secondary disk. And say if the process P1 requests some new data which is not present in this DRAM, then you go into the secondary disk and fetch it to the main memory. So on demand you are fetching it and storing it in memory, and not on the assumption not storing it in main memory always. So it's on the assumption that some pages are used frequently, some pages are not used that much. So you can use that space for some other process or storing some other information.
Okay, got it.
So that's what demand paging is. Something like a cache policy. That's it. So right. So given this thing, what they have given is the average memory access time is x. So this is your average memory access time. So average or effective memory access time. Okay, and the formula for calculating this average memory access time is um, in this demand paging scenario is, say say F is your page fault rate. So F denotes a page fault, like PF. So this is your page fault rate. So similar to hit ratio or miss ratio, PF is your miss ratio, page fault rate. That is like the page is not present in your DRAM. That is page fault rate. And now we have to find what this PF is. So the formula for finding this average memory access time, which they have already given as x units, is um, whatever is the time taken to access the memory during hit, like say that page is present in that memory, the data is present in the DRAM, that is time taken on the hit scenario into the hit ratio, right, plus time taken when it is not present in the memory into um, whatever is the miss ratio. So miss ratio as in the page fault rate, and the time miss is, say you go to the secondary disk and then store it in the DRAM. So that's what comes into the time miss. This part is time miss, and just accessing the DRAM it is time hit. Okay, and now this time hit they have given it as it takes m units, right, if it's present in the DRAM itself. So time hit is m units, and the heat ratio, since we have to find the page fault rate, the heat ratio is nothing but 1 minus pf, right. Both combined together is 100%, so this is 1 minus pf plus this time miss rate is the time taken to access the secondary disk and then get the data to the DRAM, that's the main memory and all those things. So that they have given it as D units. D units if memory access causes a page fault. So that is D units into miss ratio. Miss ratio is nothing but the page fault rate. Now if you just do split it and see m into m plus, okay, pf, and this d minus m, and this is x, and if I just do x minus m equal to pf into d minus m, and the page fault rate is equal to x minus m divided by d minus m. So this is what the page fault rate is. So x minus m divided by d minus m. So option B is the correct answer. So the question is they want to express this page fault rate based on the notations they have given x, d and m, and using this formula just you should rearrange and get the notation for this the formula for this page fault rate, right. Any doubts in this question?
Yeah.
So in that case let's move to seventh question. The question is long but the logic is simple. It's just like the wordings, it's in sentences, okay, so don't worry. So say a processor uses two level page tables for translation, for the address translation, and the page tables for both levels are stored in the main memory. So they don't use any caches to store these page tables, it's all stored in the main memory. And now the virtual and physical addresses are both 32 bits wide,
I have a question. Page
right.
tables reside in main memory, right? Or
Page tables reside in main memory, yes. Yeah, they
they
will reside in main memory.
they don't reside in cache or something.
No, so usually it depends on, no, usually it doesn't reside in cache. So that's why they get a separate TLB, right, for caching that page tables and those things. Yeah, you get my point, right? So say
Actually, in a lecture, I was saying that everything, like logical address and page tables, reside in main memory, and then we access that from there. The data resides on disk, but the page table and pages, those reside in main memory.
yeah, pages, the page table will reside in main memory, but whether they will get filled into the cache is different, right?
So the page table should be in main memory, and
No, so see, say when the CPU generates a virtual address, it should go through the page tables to obtain the physical address, and this physical address will be used to access the DRAM. Now, where will this page table? The page table also has some contents, right? Where will this be stored? This will also be stored in the DRAM only,
yeah, that's what I'm saying.
right? The why I mentioned the caches is the cache is like optimization, right? for each access, load or store operation, instead of going to the main memory, first it will check in the cache, and if it's a hit it will return back, and if it's a miss it will go to DRAM and then fetch it back. So this page table.
I just want to know that whole page table, we put this whole page table in the cache or
Yeah.
fraction of it.
So this the page table won't usually be put into the cache. For that only you maintain like a separate thing like a TLB. The one possible reason is whenever you want to perform a load request, right? You can do a load operation. As I mentioned, two steps. One, you have to translate the address to a physical address, and then you have to do the actual access. And the it depends on, so it depends on how your caches are also designed, whether you are providing the virtual address itself to your caches, or whether you are providing your physical address to your caches, and based on how your cache is designed and all those things. And the most of the caches, at least first level caches, are VIPT, right? So actually this goes into the computer architecture concepts. So when you are designing these caches, so the high level overview is you don't want to have a sort of contention between the data and your page table.
No, I just want to know, just like we define cache because we need faster access to data, right? And there's a TLB which acts like a cache for the page table.
Yeah, so
So,
the TLB is the cache,
so,
it's like a
so,
cache to the page table, right?
so TLB and page table both reside in main memory, right?
No, no, TLB is a separate content actually. It is separate.
Uh, TLB is like a separate hardware itself.
Yeah, yeah, it's a separate hardware unit. It's not present as part of the DRAM, as Nandan mentioned. So how the caches are separately present, the TLB is also separately present, the DRAM is separately present. The page table resides within the DRAM, the TLB is separate.
So in cache, we get the fraction of page table, right? Something like that.
In caches, whether you store the page tables, that's what your question is.
I'm saying it.
Uh,
We're not calling whole page table in cache, but as per the requirement, like the number of blocks of page table we need.
Right, so that's what I mentioned, right? Usually they don't try to store the page tables in caches. You can.
like,
uh,
are you asking about the inclusion and exclusion of the page tables?
Yeah, I mean, like in cache, we access data for the processor for fast access, right?
Yeah,
And page table reside in RAM.
yeah,
So
yeah.
uh, cache will be more closer to processor. So I
Yes.
just want to know that whether page table, I mean, fraction of page table will be taken to cache and then access
No,
the.
no. Like the fraction of page table will be stored in the TLB. TLB is a cache. Okay, it's a separate cache from the L1 and L2 cache. Okay, TLB is a cache just for storing the page tables. Most access like
So
most accessed the
the processor will be accessing this from the TLB, not from cache, in case of page table.
like once you get a request from the processor, right, so like it will go to the MMU. So the MMU first check the uh, TLB. If there is a hit, it will like give the frame number. Else else the request will be go to the page table, and then you will get the frame number.
Okay, so in case of page table, it does the processor doesn't seek caches, right? It goes through MMU and TLB.
Yeah, yeah.
Okay, thank you.
yeah. No, so just adding to Nandan's point, right? Why it is designed in such a way, one reason is to maximize performance. You can very well store your cache, the page tables in the caches also, as you have mentioned, Sashikant. But what happens then is you You just do it in, you should do it in a sequential way then, because your, say your cache is there, and the cache can just handle, say, one memory access, one memory request. Okay, so first you should go and search for the page table in the cache and then memory and all those things, and then only you should go and search for your all the once you get the physical address, then you again go to the cache, search in the cache or not, then you go to the main memory. So the system is designed in such a way that this first step, right, which is the crucial step for the address translation, it need not rely on the cache for caching. Instead of that, they just have a separate cache mechanism for this page table itself. So the address translation goes by this way and then it comes over here. So they just split that step one to maximize performance. So there is no wrong in storing the page tables in cache. Only thing is, you give multiple requests to the cache unnecessarily, and it just increases your time to go and fetch and data after doing the address translation. Everything becomes sequential. You cannot do any parallelization or something in the operations.
Okay, got it.
So in that case, let's continue with the question. Okay. So it is given, it uses a two-level page table, and both virtual and physical addresses are 32 bits wide. The memory is byte addressable, and for virtual to physical translation, 10 most significant bits of the virtual address as used as index into the first level page table, with the next 10 bits as used as index into second level page table. Okay, so this is the 32 means 10, 10 and the remaining 12. So this one is used for index into the first level page table level 1, and this one will be used into second level page table level 2. Okay, and finally this 12 least significant bits will be used as an offset into the actual page. Okay, so now 12 least bits. Assume that the page table entries in both levels of the page table bytes are 4 bytes wide. Okay, so each page table entry is 4 bytes. Okay, and now further the processor has a translation look aside buffer. Okay, TLB caches. So it has a hit rate of 96%. So this is not wanted in this question. So this is not wanted. TLB caches, physically addressed caches. Okay, this part all no need, is not required. Um, Main memory access time. So till this part it's not required, right? These 4 lines are not required, it's not related with the question. And now say, starting from here, suppose a process has only the following pages in its virtual address space. They have, so what all pages are there? Two code pages, two CP, starting at the virtual address 0x 0000. Okay, and the other thing is 0x. So two code pages, okay, contiguous code pages, and two contiguous data pages. So this is what is required by our process P1, and
There is a difference between two
okay,
continuous
okay,
data pages
yeah, okay,
Actually,
okay,
the second one is the
okay,
stack
okay.
page.
Sorry. In between, yeah, okay. So one is present at 0x004 0, and the other is at okay. So 1 dp, and the other is 0x ff 000. Okay. So now they are asking what's the memory required for storing the page tables of this process, right? So how we approach this question is, we have to find the so L1, since it's like two level paging is being used, and the number of offset bits into a page is 12. So the page size is 2 power 12, which is 4 KB. Okay, and we assume that the page table, so each page table size is also aligned, as in each page table size, this one is also page aligned only 4 kb, we assume that. And now if we see, um, always irrespective of where your memory is allocated, right, there will always be only one level 1 page table. This is common for all these things. Okay, so this level 1 page table for sure it will be allocated. So L1 page table for sure it will be allocated, that is 4 kb. And from this 4 kb, now we have to see how many level 2 page tables should be allocated. Okay, so the level 2 page tables, how many it would be allocated depends on whether the entry, the index offset into this level 1 is different for all these addresses, right. We have three addresses, one A1, A2 and A3. Okay, so whether the starting most significant 10 bits, whether they are the same or different. So if it is the same, right, then it indexes into the same page table entry of L1, which points to the same starting address of the L2 page table. If it's different, then it will be utilizing two different L2 page tables. Okay, so if we take the address A1, the starting 10 bits is all 0. Okay, so for address A1, it is the 10 bits, the index into the L1 is 0. So, and for address 82 is also, if you just take 0 0, and this is also 4 is 0 1 0 0.
It's the next entry, right?
It's a next entry. So it uses the, say it is like the 0 entry, it's the first entry. And now for address 83 also it is different. It will use the second entry.
Can you please explain like why you taking 3 digit here?
Why you are using?
3 digits like 30.
Actually,
No, it's not three
the
zeros
address
as
is
in,
a like
yeah,
hex digit, right? So like each digit like
4 bits.
change the 4 bits, yeah, four
So
binary bits.
yeah, so each is 4 bits. This is,
Got it. Got it.
yeah, so 4 4, and this is actually like you take the half root. So that's what. So see, you are using one entry for A1, A2, and then for A3. And now these two will be for will be three different L2 uh, page tables. Okay, these three will be different L2 page tables. Okay, so number of L1 page tables is 1. The number of L2 page tables is 3. And now from L2 page table directly you would be using, you would be getting the physical address, since it's just 2 level paging. So the number of page tables that are being used is number of L1 plus the number of L2, which is 1 plus 3 4. And each page table is of the size 4 kb, so it is 16 kb. So the answer is option C, 16 kb. Do you get the idea
Okay.
how solve the question?
Yeah, got it.
Right. So, yeah. Nandan, any query in this?
No, sir.
Okay. Yeah.
Nandan in the final year?
No,
Sorry.
like I'm passed out.
Oh, okay. Oh, nice. Yeah. So in that case, let's just move to the eighth question. So it is given you have a two-level page table for virtual to physical address translation. So you are having two levels, that is the info 1 they have given, and both are 32 bits wide. Okay, and the memory is byte addressable. Okay, it uses 10 more significant bits and 10, okay, same as previous question, it uses 10 bits and 10 bits to access each of the tables, and the page size is 4 kb. 4 kb is the page size, and each page table entry is 4 bytes. Okay, right. So actually this information is not required for this question. So I'll start from this part. So it's actually the same question, I guess, but okay, they are asking the access times in this question. So assume that the page table entries in both the levels of page tables are 4 bytes wide, and the TLB has a hit ratio of 96%. Okay, so the TLB hit ratio is 0.96, and the TLB caches use virtual page numbers. Okay, the processor also has a physically addressed cache with a hit rate of 90%. Okay, so now your cache's hit ratio is 0.90, 90%, and the main memory access time, so accessing your memory is 10 nanoseconds, and the cache access time, so cache access time is 1 nanosecond, and your TLB access time is also 1 nanosecond. Okay, so assuming that no page fault occurs, okay, so everything is present in your main memory itself, there is no secondary disk or something. Find out the average time taken to a virtual address, right? So we have to find the average time taken to access a virtual address. Okay, so the how we approach is as we discussed, right? Step one, so here they have not given any information of whether accessing the TLB and the cache occurs parallelly or not, or all those things. Okay, so we assume that we have to first, step one, do the translation. Okay, so virtual address to physical address, and step 2, we have to access the cache or memory, so access using the physical address whatever we obtained. Okay, and all this, once step 1 occurs, then only step 2, so it is sequential, it doesn't occur parallel or something. Only when step 1 occurs, you go to step 2. Okay, so what we can do is, we can just draw, we can just do like a case analysis in same way. So say you are having case 1, you are having a TLB hit, right? You are accessing the TLB always. How can we go about this? Uh, this one, uh, this one, right, you can do step by step itself instead of like combining both these steps, right? Let's try doing step 1, step 2 separately. For step 1, what's the access time using this TLB hit ratio and the TLB access time and this memory access time? If it is hit in the TLB, it is 0.96, and in that case you just utilize 1 nanosecond of the time if in the hit scenario. If it's a miss, what happens? The remaining 0.04 times, what you have to do is, you will be accessing your TLB to find out it's a miss, and you have to then access your page table which is present in your main memory. And accessing the page table, you are using a 2-level page table. So first level you will be accessing, and then second level you will be accessing to get your physical address. So 2 times you will be accessing your main memory to get your final physical address. So 20 milliseconds, so 10 into 2, you will be to 20 nanoseconds, sorry. Okay, so this is your step 1, you will be utilizing this. Okay, and step 2, once you get your physical address, you will access the cache using that physical address. And what's the hit ratio? It is given 90%. So for 90% of the time, you will be just having 1 nanosecond access time, and for the remaining um time, you will be utilizing, you will be for the remaining 10% time, it will be a miss. Okay, for the remaining time it will be a miss, and you will be accessing the cache also in that miss scenario, because to find out whether it's a hit or a miss. But the remaining time, the extra time, you will be accessing the memory, which is 10 nanoseconds. Okay, now both these steps together, step 1 and step 2 will give you the actual access time. Okay, so can anyone just, did anyone calculate? Okay, 0.96 plus 0.04 into 21, 04 into 21 plus 0.90, so plus 0.90 plus 0.1 into, what's the remaining, 11, so 3.8. So 3.8 nanoseconds is the actual access time, considering you get translation first, get the physical address, and then you access the cache or the memory based on the hit scenario in the cache. So 3.8, and you have to round it off to the nearest 0.5 nanoseconds. So 3.8 round off, it's 4. So the correct answer is 4 nanoseconds. So any doubts in this question?
No.
Right.
Clear.
Nandan, any doubts?
No.
Okay, cool. Then in that case, let's move to the ninth question. Okay, so it's given a processor uses 36-bit physical address and 32-bit virtual address. Okay, so the VA is 36-bit and your physical address is 32 bits. Okay, and the page frame size is
Actually, it's reversed, right? Uh,
sorry.
like
Oh, okay.
36-bit. Yeah.
Oh, right. Sorry. 36-bit physical address. Is the mistaken question or what? The question is correct only. Sorry.
The question is correct,
Yeah,
actually.
question is correct. Yeah, I misread it. So it is. Thanks for pointing it out, Nandan. Uh, it is 32-bit, and page frame sizes. Frame size is 4 KB, right, which is 2 power 12, and each page table entry is of 4 bytes. Right. And now a 3-level page table is used for the virtual to physical address translation, where the virtual address is used as follows. Bits 30 to 31 are used to index into the first level. Okay, so number of bits required for addressing the next level page table. So the thing is, they have given this virtual address, and out of this 32 bits in the virtual address, the first 2 bits should use to access the L1 page table, and the next 8 bits, is it, no, 9 bits. Okay, the 9 bits is used to access the L2 page table, and the next 9 bits for the L3 page table, and this final 12 bits is to access into the page whichever you get the physical address. Okay, and is to index into, okay, and 0 to 11 are offset. Now the question is, each page table entry is of 4 bytes. We have to find the number of bits required for addressing the next level page table in the page table entry of first, second and third level page. So this L1 would be one page table entry is of 4 bytes, that we know. But within this 4 bytes, some would be like, say, permission bits, and whether it is kernel or user space and all those things, that extra information. I have to find out the minimum number of um, bits required, so that I have to get the um, I have to use that as a physical address to get my L2 page table. And similar way, when I'm using this 9 bits index into the L2 page table, whatever entry this part of the field is offsetting into the L2 page table, this will be storing some physical address which denotes the L3's page table base address. So how many minimum bits should I be using to properly access that L3 page table? And within this L3 page table, some entry bits should be used to actually denote the actual physical address of the page size, which is of 4 KB. So what's the minimum bits used for addressing? So that's the question is. And one key thing to note in this question is, even though they have given the page frame sizes of 4 kilobytes, right? So it is, so for 4 kilobytes, so 4 bytes in the sense each page table is 4 into 8, 30 minus 12, 4 bytes.
I think 24, like
Yeah, yeah.
2 per 24.
Yes. So for the last level 3, right, 2 power 24. The reason being it is, uh, wait. I just got confused with these numbers. 1 second. L3 is 4 kilobytes. Now, kilobytes. So it's based on the thing, right? You have 2 power 36 physical pages, right? And each page size is of 4 KB, which is 2 power 12. So the number of pages is actually what 2 power
2 per
24.
24. Yeah.
And so based on this, uh, the number of bits that you have to
Like
add, sorry,
number of page frames, right?
yeah, number of page
Yeah.
frames is 2 power 24. And to individually access each page, you should be requiring a 24-bit identifier, right? So that each of these 2 power 24 bits you can find out. Sorry, 2 power 24 pages you can uniquely access from this L3 page table.
Yeah.
So for that, in L3, out of the 4 bytes page table entry, that is 32 bits, right? 24 bits would be used to access to denote any one of these 2 power 24 pages. So for L3, which is 24,
Can you please repeat that?
right? So the question is asking for what is okay. So just to reframe it, right? They are asking the number of bits required for addressing. That is the number of bits which denotes the frame number in your page table. So the final thing what your page table does is whatever you give your page number, it will output a corresponding frame number, and using that you get your base address of the page, and then you use the 12 bits offset right into this frame. And they are asking like what's the number of bits in this frame number, whatever is being stored in each of these level uh, L1, L2 and L3 page tables.
Okay.
And the thing is, um, the memory is split into pages that is used for normal data, but for the L1, L2 and L3 pages, sorry, the page tables, it need not be memory aligned. So they follow that assumption because the page
What
tables
what
are
it
directly
memory
used by, sorry.
what it mean by memory line?
So memory aligned means say each page is of 4 KB, right? Your page table also, then is it the case that that page table should also be stored in a page, or it can be of any size? So that's what is memory aligned.
Okay.
Okay, so just first considering L3, right? What's the size of the frame number bits which are being stored in that page table entry? How you go about finding is you have to find out the total number of page tables, sorry, total number of pages that is present in the virtual memory. So how do you get it is the page size in the denominator, and in denominator you have the total, the physical address space, right? So those many physical pages are present. So 2 per 24 physical frames are present actually in the physical memory. So to uniquely identify any of those frames, you have to use at least 24 bits to uniquely identify any of those pages. So in that L3 page table, for addressing the next level page or the actual page, you will be requiring 24 bits of information. So if we just you look at the L3 page table, that information, it is 24 bits. So option A and C are um, we can cancel those A and C options. So it's either B or D. Now coming to L2 and L1, right? So for L1, okay. So here for L2, if you notice, it is using a 9-bit offset for indexing into L2. So the formula to find L2 is the addressing scheme for L2 is the number of L3 page tables. Okay. Number of L3 page tables. So we have, then since we have to just a second. So we have 2 power 36 and 2 power 9 entries, and each entry 2 power 9 entries, and each entry is of 2 bits. Okay. So to find out the addressing scheme present in L2, right? What's the technique? The thing that we have to find in L2 is what information that an L2 page table entry will contain. So it will contain one, the permission bits and all those things. That is one. And the second, what it will contain is, it will contain the frame number of the L3 page table, right? You get this, right? This till here you understand, right?
Yeah, yeah.
The L2 page table entry. Now we have to find out how many bits I should require to um, represent this frame number. So as in, just rephrasing it, right? The number of frames that might be possible where all these L3 page tables are located. Right. So if we get the where number of frames in this L3 page tables, right? The number of frames these L3 page tables occupy, you will
It should be number of frames or number of entries, basically. The next
Actually, if
row.
you call like page
so
table
actually,
number,
yeah. So it's number of entries only. So number of entries. No.
I mean,
No, no.
it's like a chain. So the previous page table will focus to the entry of the next page table and so on.
Yeah. So the L2 entry will point to a L3 page table, right? So 2 power 9 entries into page size. Okay. So okay. Sorry, I'll just reframe this. Okay. Sorry for the confusion. The formula we have to find is, we have to find out the number of um, the number of frames, right? 2 power 36. 2 power 36, and we have to find out the number of L3 page tables that might be present. Okay, based on this only we can once if we find this, the corresponding bits we have to represent it in the frame number in the page table entry of L2, so that it can uniquely identify any one of these L3 page table entries. Now it's clear, right?
Yeah.
Okay. So the number of L3 page tables I should find out. Then only I can find out the frame number bits that will be stored in the L2's page table entry. So for finding out that, what we have to do is the number of each L3 page table is of size 2 power 9. How we get it is we are using 9 bits only, right, to offset into L3.
Yeah.
So to offset into L3 we are using 2 power 9. So that is each page table is of 2 power 9 only. And to get the number of L3 page tables, the formula is the total physical address space divided by like assuming that the whole physical
Like
memory.
number of entries into the size of one entry, single entry.
Exactly. So 2 power 9 is the number of entries, and each entry is of 4 bytes. So that is 2 power 36 minus what's 11, which is 2 power 25, right? 20, yeah. So 2 power 25 number of L3 page tables are present. Now to uniquely identify these 2 power 25 L3 page tables, you should have that many bits in your L2 page table to uniquely identify one of these L3 page tables.
Yeah, the same is the case for the N1.
Yeah, so 25 bits
Right.
information you should be using in your frame number in L2 space table entry, so that when you do the address translation, it identifies one L3 page table, and then you use the 9 bits of the L3 to offset into that L3 page table.
Yeah, got the question actually.
Yeah.
Clear.
So that is for L2's addressing scheme, and in the same way for L1's addressing scheme, you have to find out the number of L1 page tables. Sorry, number of L2 page tables.
So again, there are 9 bits allotted and every.
Yeah. So again, it's the same. So 2 power 36 into, so it will be 2 power 25. So the answer is for option D, 25, 25 and 24. So for the L1 scheme, it should be using 25 bits information to identify which L2 page table it has to use out of the 2 power 25. Again in L2 it will be utilizing 25 bits to identify which L3 page table it has to use, and in L3 it will be using 24 bits to identify one of the 2 power 24 pages it has to point to. Do you get it?
Okay, got
Right.
it. Thanks.
Okay. And the thing when I said about aligned, as in here the size of one page table in L2 or L3 is 2 power 9 into 2 power 2, which is 2 power 11. In the question it's given 2 power 12 is the frame size, but here the page table size is 2 power 11. So here they assume that for optimization, right, for efficient usage of memory, you don't fill just allocate, they just uh, remove that internal fragmentation, this unused space, they don't want to have that. So all the thing is just like variable memory allocation for this page tables alone they do.
What if it's not aligned like
So if
the
it's no, so here it is not aligned. If it's aligned as in, then 2 power 11, the thing is, if it's aligned means then it will be different, right? You will be using just 24, 24, 24 for each thing,
okay.
or something like that. Yeah. 24, huh? Yeah, something like that only will be utilized. You won't be utilizing 25 bits for the frame number in L1 and L2. 25 bits you won't be using. If it's aligned, then aligned as in, um, yeah, if it's aligned means then you will be utilizing 2 power 36 divided by 2 power. No, so even, okay. if it's aligned right, um, okay, if it's aligned, then what happens is your page table size will be this only, 2 power 9 into 2 square, which is 2 power 11. This will be your page table size always for L2 and L3, these things. But the thing is the remaining memory. So 2 power 12, what's the remaining memory? Uh, uh, what's the remaining memory, right? 2 power 11 is the remaining memory. So it just gets doubled, right? So 2 power 11 memory is just left out. So you won't be using that extra memory anywhere. It's like internal fragmentation. You are just wasting that memory space. Or you can do some optimization or something to keep these page tables together.
Okay.
Yeah. So Nandan, any doubts in this?
No, sir.
Okay. So in that case, let's move to the final question. Okay. So it's given a computer uses 46-bit virtual address, 32-bit physical address. Okay. So the virtual address is 46, physical address is 32, and they use a three-level page table, L1, L2, L3. Okay. And each page table based, the page table based register stores the base address of first level table, okay, which occupies exactly one page. Okay, so T1 size is one page, and each entry of T1 stores the base address of a page of the second level table T2, right? And okay, and each entry of T3 stores a page table entry. The PT is 32 bits in size. Okay, so the PT is page table entry is 4 bytes. Okay, and now the um, okay, so this part is not required. The last two lines is not required. So just till here. So it's given each entry of T3 stores a page table entry which is of 4 bytes. Okay. Uh, right. The question I'll just now the question is, what is the size of a page in KB in this computer? Interesting. Okay. So they have given this information as in they have given the 46-bit virtual address space, and they have given this information 46-bit virtual address and 32-bit physical address, and they have given L1, L2, L3. All these things they have given L1, L2 and L3. Okay, and now we have to find out the page size, and the only thing that we know about what a page size is, the L1's page table is also just one page size only. So assume you just assume like a page uh, size is p bytes, or p bytes or something, p bits, just for okay. So assume it to be p bits. That's what your page size is all about. And now it is given the L1 size. The L1 level 1's page table is also p bits. Okay. Now, how can we use the following information to get what this P stands for? We know the 32-bit to power 46. So, okay. So we know for sure the number, it's a 46-bit virtual address. So based on this, what we can infer is the maximum number of page table entries in the um, uh, third level table, right? So in the third level table, so you will have a set of page tables in level 3. All these level 3 page tables together will be pointing into somewhere within this 2 power 46 bit virtual address space for sure. It's in like, say your page size is p bits, right? So 2 power 46 by p divided by p is the number of pages present in your virtual address, and all your L3 page tables, all these put together, all the L3 page tables entries, each one of them would be pointing into any one of these pages only, 2 power 46 divided by p. Okay, so if we find a formula which connects the number of entries in L3 to this number of pages, right, then you can find you can try to find out what this unknown p is. So what we'll go about doing is, we have to find out the number of entries present in the L3 page table. So how do we find out the number of entries in L3 page table? We have to start from the level 1 page table, because there is one level 1 page table and then you have multiple L2, and each L2 can have multiple L3, right? So all these things put together is only this number of L3 entries. So we have to find out starting from L1. So the number of say the L1 entries, right? Say the L1, it is given page size only. So each is of 4 bytes page table entry. So the number of L1 entries, the number of L1 entries is nothing but P divided by 4 bytes, which is 2 power what's that, 4 bytes is 4 into 1 byte is 8 bits, 32 bits, right? So 2 power 5, is this correct? 2 power 5, yeah. So the number of entries in the L1 page table is this much, P divided by 2 power 5. The P is page size in bits, and each and number of entries is this much, and this means like this is the number of L2 page tables. Just rephrasing it, right? The number of L2 page tables, and assume that they have not given any information about the level 2 page table or something. So since they have just given information that the L1 page table is of size this much, it's equivalent to page size itself, so we assume that the L2 is also having, the L2 page table also occupies the same page size, that is p bits. Okay, so now to find out the number of L3 entries, we have to find out the number of L2 page tables into number of L2 entries in each L2 page table. And the formula is, for this we have a P by 2 power 5 into number of L2 entry in each L2 page table is the same actually, if you just use the same formula again. So that is the number of number of total number of L2 page tables, which is nothing but the number of L2 entries. So we get the total number of L3 page tables, which is P to the power 2 power P by 2 power 5 d whole square. So P by 2 power 5 d whole square, you will get it. And now so this is the total number of L3 page tables. Okay, and to find out this small p, right, whatever we have over here is the number of pages, and this number of pages corresponds to number of level 3 entries. And to find out that is the number of level 3 entry is nothing but the number of L3 page table into each entry that one page table has in L3. So it is nothing but P by 25 d whole square into P by 25. So again, assuming L3 page table is of the same page size, so you get
Yeah, how we calculate the last one?
for 5, sorry, not 25. Last one. No, you get the number of L3 page tables. Okay. Now we have to find number of L3 entries in that last level page table. How you get that? You have the number of page tables in L3 level and the number of entries in each page in each L3 page table. You just multiply that.
Okay, okay.
So you get p to the p by 2 power 5 the whole cube. Now what you can do is you get this. So this is the number of entries in L3 and the other notation is number of pages, right, in the virtual address space, which is nothing but 2 to the power 46 divided by p. So now what you can do is 2 power 46 by p is equal to p by 2 power 5 the whole cube. You equate both and if you just do that, you will get p to the power 4 and bringing this 2 power 5 to this side, 2 power 46 into 2 power 15, which is now p power 4 equal to 2 power what's that, 46 plus 15, um, 2 power 61, 2 power how will this split? Did I make some mistake in between? It is p bytes. If I assume it has p bytes. Okay. So the thing is, this 2 power 46 by p, right? This denotes this 2 power 46 as in its virtual address, and each is like byte addressable. Uh, so that's what a normal system is, right? Like each address, that 46-bit virtual address points to 1 byte of data. So here it's actually when I uh, so here I should probably just p bits means I need not convert this 2 power 5 this 4 all into what this 4 bytes I need not convert into 2 power 5. That's the so if I just use it as 4 bytes itself and this p bits, just give it in the terms of p bytes. So let's try it then. It's p bytes and then this is just 4. So in that case p power 4 is equal to 4 cube. Okay, so p power 4 is equal to 2 power 46 into 2 power 6, which is 2 power 52, and in that case p square is equal to 2 power 26 and p is equal to 2 power 13. So this is the page size in bytes, which is 2 power 13, which is 8 KB. You get it right? So the final thing, like where I made a small mistake is initially I had just mentioned the page size is represented in p bits. So in that case, what I should have done is in this formula, um in this final formula, I should have since this 2 power 46 by p represents in bytes actually. This thing, this p bits, I should have divided by 8. This p by 8 actually. So that's the small mistake. So just assume from the start we represent p as in page size as in bytes, and this 4 bytes of page table entry we just don't convert into bits. Okay, and just apply that same logic whatever I did. So find the number of L1 entries and then the number of L2 page tables. Based on that, find the number of L2 page table entries, and based on that, find the number of L3 page tables. Then multiply it, you will get the number of L3 entries, and that is equivalent to the number of pages in the virtual address space. And if you equate both, you will get this unknown p, and this p is nothing but 2 power 13, which is 8 kbs.
Okay.
So the option correct answer is option C, 8 kbs.
I have a just question like how you so comfortable in capturing these complex questions. I mean,
No, no. So these things, like actually, thankfully, you just the answers you had mentioned. So working towards such answer was a bit easy actually, but yeah, once you get the concept right, it's easy. Like it's somewhat tricky, but thing is, you should be clear in your concepts. That's it.
okay.
So that's the only thing. So these things are all just again and again they just use multi-level page tables and the number of entries, those things.
Is there any recommendation like you can suggest me so that I can study numericals from there
No, no,
to be
I just
more comfortable?
no. So actually, you had posted questions related to virtual memory, which I was a bit comfortable in. If and since you had just posted it, I just noticed your mail today, and I just went through these questions and added these to the slides. But the same, if you are done for some other concept as in deadlock or synchronization, it would have been difficult for me because I'm not solve those questions much, right? So
Okay.
it's just like concept wise, you should be clear. That's it.
Okay. Thank
And
you.
yeah, Nandan, did you understand 10th question? Any doubts?
Actually, it's like I was in some other meeting. I'll check the
Yeah, yeah, sure.
recorded video. Yeah.
Yeah, sure. No issues. Then in that case, we have reached the end of the thank you slide also. Okay. So
It's a quite long session, and I'm very thankful for you to giving your
yeah,
time.
it's okay. My pleasure. So the requirement is just I have to teach 1 hour, but anyway, I enjoyed discussing these tough questions too. That's why I didn't mind spending some extra time. Yeah. Thanks, Sashikant, for sharing these extra questions.
Thank you so much.
Yeah. Next time, like if you want to share it again, just ensure that you share it at least 2 days before.
Okay.
I
Sure.
get some time to
Yeah.
prepare
Sure.
also.
Sure.
Okay.
Actually, I was not clear with your email, so I just tried and I hope that I'm
Yeah, yeah. Actually, it went into the spam folder. So
okay.
yeah, since it's outside my institute accessibility. Yeah.
Okay. Thank you.
Okay then. Thanks, Ashikant. Thanks, Nandan. Thanks for making it interactive. See you.
Thank you, sir.
Yeah.